day 4, section 5. So today I'm going to talk about what might be future fuels in our energy system. There's actually not going to be a huge amount of chemistry in today's presentation, but I don't know, I find it quite interesting to try and have a vision of what the future energy system might look like. It's actually not a very easy thing to do because I don't think we've yet settled on a strategy internationally or nationally in the UK. And there are a huge number of different options, and obviously I'm not going to cover them all today, but I just want to give you a flavour really of what future fuels might look like within the overall energy system and what that might mean in terms of combustion science. So I guess the reality is, well, historically, combustion has made up, a very large part of our energy supply. From about the 1950s onwards, as the world has kind of developed since the end of the Second World War, the utilisation of energy has grown massively. I guess, first of all, in the West and in Europe, and more recently in China, India, Middle East and countries, etc. And so I guess what people are always telling you is coal combustion's been used for decades and we'll still be using combustion for more decades. But the reality is this continued use, unabated, of coal, crude oil and natural gas that has grown so much over the last 70 years cannot continue unabated because we will never get to the goals of the Paris Agreement, which is to get to net zero by 2050. But why are we finding it so hard? I mean, the reality is that actually these fuels are quite easy, relatively easy to extract and relatively easy to use, even though actually for the most part we're not using them at huge efficiencies. And so it's quite a difficult habit to break. But basically, unless we put more effort into energy efficiency and reducing our demand, then we've got an awful lot of energy demand to replace. And I don't think that carbon capture and storage is really going to offset this huge amount of fossil fuel energy that we currently have. So we're looking towards new energy systems. Actually, sorry, I've added a new slide in, and I'll go back to the one that's in your notes. I have made a few tweaks today. Apologies for that, but just to make a point. So this is what the energy generation looks like in the UK. And actually, remarkably, we've actually made quite a lot of changes in our electricity power supply system over the last 10 years. There's been a hugely rapid growth in offshore wind and also in solar, although that hasn't grown as rapidly as perhaps it could have. So, I'm just thinking really of when I started looking at the CO2 intensity of our power grid in terms of kilograms of CO2 per unit energy. And we started out, I think, when I first started lecturing on climate change at about 550, and now we're down to about 200. So we've more than halved the carbon intensity of our electricity grid in the UK over 10 years, very rapidly. But now we're kind of getting to the stage where it's becoming difficult to utilize energy, and the offshore wind industry is growing still, which is a good thing. So the problem is that if we look at our daily supply, then of course it's intermittent because solar, we know, of course, is only during the daytime, and in fact will vary depending on weather conditions. So when it's cloudy like it is here today, then obviously the supply from solar will be reduced. And wind also fluctuates according to the climate and the daily solar cycles. And so some days we have a huge supply of wind energy in the UK, but other days we get calm conditions where we get very little energy from wind. We've got a nuclear baseload and a hydro baseload. And in the UK at the moment, when wind is low, we have to top up with combined cycle gas turbines. So as we grow our wind capacity, then this intermittency as an overall part of our grid is also going to grow with it. And that creates problems because some days in the UK, we create wind energy that we can't actually transport through the electricity system and we can't use. And I was actually quite surprised when I looked into this further to learn that on 75% of days of the year in the UK, we actually curtail wind energy. So we've got wind energy available, and we're just throwing it away. And that's clearly going to get worse as we bring new offshore wind farms online. So that's one challenge. The second challenge is that there's an offset in, well, so at the moment in the UK, I'm not sure what the US system is, maybe some of you can tell me, but we supply most of our heat, both domestically and for industry, through natural gas. Okay, so I still have a natural gas boiler, as do the majority of the population of the United Kingdom. And, you know, okay, condensing boilers are relatively efficient compared to an IC engine, but still, that's an awful lot of demand for energy that we have to replace. So what are the options there? Well, we can use electricity to supply heat, both industrially and domestically, or we can move to carbon neutral or zero carbon fuels. So hydrogen might be an obvious potential choice for providing heat if we can provide the hydrogen in a low carbon way. So the plan in the UK is actually to more or less move to electrification of heating in domestic settings by using heat pumps, which are much more efficient than combustion devices because they can get to efficiencies of a factor of 3 compared to the electricity that goes in. So for each kilowatt hour of electricity that you put into a heat pump, you get 3 back out as heat. So because the rest is coming from the air. So that's great because that reduces our overall energy demand. But our heat demand, of course, is in the winter months and usually in the evenings when the sun's gone down, right? So we have a massive mismatch between the electricity that we'll be supplying from wind and solar compared to the demand that we might make from using heat pumps to heat our houses. So one way or another, we're going to have to do something to store energy. And, well, I mean, I don't know how many of you get involved in Twitter and energy debates on Twitter. I find it quite a fascinating place to hang out. So, because basically there is a raging row going on between people who believe that everything should be electrified and people who believe that low-carbon fuels have a role to play. And these are very polarized positions, as far as I can see, on Twitter anyway. But, yeah. But actually, even I think in the real world. And so there are people who fully back hydrogen as a future, and there are people who say that it's a red herring. And actually, I'm interested in this, and I've done some work on wind energy as well. And so I got a master's student to look at the overall energy demands of using heat pumps versus hydrogen for the UK. The overall electricity demand from using hydrogen is substantially higher because your hydrogen system is at best probably 90% efficient, whereas your heat pump system is 300% efficient. So it's very hard to compete. But what the heat pump people don't talk about is how are we going to supply that electricity at times when our generation system is not going to be generating. And then, you know, they start to say, oh, we will have vehicles that will be connected to the grid and they'll have batteries. This is not going to work, right? That might give you a storage over 12 hours. But in terms of heat demand, you know, we're looking at storage at least over weeks and potentially longer, right? Because, you know, there are long periods of time in winter when it isn't windy. And there are long periods of time when we have very high power production from wind. And so we need to balance those things. And this is not a daily cycle. This is a long-term cycle. Okay, so, I mean, if you look, if you do a Google search for wind intermittency, it's normally fossil fuel sites that are saying, look, you know, the wind's intermittent, we shouldn't be using it. And that's not what I'm saying. What I'm saying is that we need to tackle this issue about energy storage urgently. So I probably should have put a slide like this in your notes, but this is the slide that's in your notes. And now looking at what the potential for energy storage might be. So we've got a whole range of different options, What this graph is showing is basically the energy density as a function of volume compared to the energy density as a function of mass. And actually, so therefore, the most energy-dense fuels will be at the top here, and of course, they're nuclear fuels. And one of the reasons why we're kind of stuck with oil and coal, or we find it hard to wean ourselves off these, is because they have very good properties for storing energy, right, both in terms of volume and mass. I mean, actually, natural gas has high energy density in terms of the mass, but relatively poor, obviously it's a gas, so relatively poor in terms of the volume. And I think I showed this already earlier in the week, but hydrogen, of course, is even worse because of its lower density. Okay, so we'll maybe think a bit more about this later, but hydrogen is going to need some kind of compression if we're going to use it in a storage system. And then other options that we've got that we might be thinking about are, of course, batteries. And there's a huge amount of effort going into improving battery efficiencies, which we are going to need. Compressed hydrogen has relatively good properties, but there's an energy cost in terms of compressing it, obviously. And then we move down to other methods like flywheels, which have very short storage times, compressed air, thermal storage. There are lots of different options. But you know, the reality is that solid and liquid fuels are very effective in terms of energy storage, both in terms of mass and volume. So should we be thinking about alternative fuels as a way of storing electricity? Well, on the one hand, that would be good because we've already got all the infrastructure to store fuels, and maybe we'll talk about this later, but maybe we can even tailor fuels to look like the systems that we have already, fuels we have already, so we can use them in engines that we already have or gas turbines we already have. But I guess the other question is who's pushing this argument, and is it locking us into using fossil fuels for too long? Any comments on that? I mean, personally, I think as combustion scientists, we should be thinking about these overall questions as well as the fundamental question that we're working on every day in our lab or at a computer. I find it fascinating. So one of the main issues that we'll have to grapple with is this issue of storage timescales. And here, combustion-based technologies or gaseous and liquid fuel-based technologies have some advantages. So chemical storage of energy is very good for long-term storage. We have facilities already to do that. And if we look at some of the other storage techniques, then not so much. So flywheels are of the order of minutes. So it's useful for restarting a grid, for example, or providing grid stability, but not that useful for providing winter heat. Same with batteries, useful for overnight storage, useful for vehicles where you can charge up overnight and use your vehicle the next day, but not going to be very useful for helping us out, providing an overall seasonal balance. And then we've got other techniques like compressed air or liquid air storage or thermal energy storage that are improving now and are kind of pushing up to several days worth of storage. But the advantage of fuels like hydrogen or synthetic liquid fuels or ammonia that I'm going to talk about today, or even biomass, are that, that we can store them for months. And that's what we're going to need, weeks at least, I would say. Okay, so I think what I'm saying is that our future fuels are going to be part of an energy storage system. And without that, we're never going to decarbonize our energy use. And my personal view is that, I don't know about the US, but in the UK, I think we're really very slow to realize this need for bringing storage onto our grid. I mean, I don't know any of you got comments about other countries. Can you shout? Sorry. Okay. Right, so you're not leading the show in the US is even slower. I mean, I think in the UK we're coming to a crunch point now because there are times There are times, hours in the year where we have excess renewables. You know, so if you're charging an electric car at the moment and you have an agile tariff, some nights they'll pay you to take the electricity off the grid. I mean, okay, we won't go into the UK energy market; it's a mess. But so we're already pushing into that situation, and so you know, why are we throwing away renewable energy? We should be facilitating storage techniques, and that could include making hydrogen. Long introduction. So changing the energy economy from fossil carriers is going to be needed. I mean, I'd be delighted if CCS proves itself to be rapidly applicable, but I suspect that that's not going to happen overnight. So we do need to move away from fossil energy carriers to renewable energy fluxes. And the main challenge then is efficiently to convert renewable energy into electricity and either store the electricity or then to convert that electricity to some kind of synthetic fuel and store that. Now the problem here is going to be the word efficiently. So as we move further down the conversion chain, of course, the efficiency is going to keep decreasing. So we can produce hydrogen through electrolysis, and that's got an energy cost. We might then convert that hydrogen to ammonia, and then back again to hydrogen to burn it or use it in a fuel cell. There's energy loss there. And actually, you know, making synthetic fuels, synthetic liquid fuels, is way down the efficiency curve. I mean, efficiency isn't everything. The two really important things are how much CO2 can we reduce, or greenhouse gases, and how much is it going to cost? I mean, solar is pretty inefficient, but it's cheap, despite that. So efficiency isn't the only holy grail, but cost is going to come into this. Okay, so a quick run through one or two things I'm going to talk about. Hydrogen, then, we can produce cleanly from water through electrolysis, and actually we can do that from seawater as well, so it doesn't necessarily have to impact on water availability. So we've got methods to store this. I mean, in the UK, we're looking at using salt caverns, for example, and it can actually be stored in the gas network as long as we're not storing it in steel pipes. And you know, when we burn it, we've got no CO2, we've got no CO, no unburnt hydrocarbons because there's no carbon in the fuel, obviously no soot. So we just have to come up with low NOx strategies to be able to use it effectively. So the cons of hydrogen are that storing it's a challenge because of its low density, and so we're going to have to compress it in some way to store it, or maybe convert it to something else and back again. So one way, I suppose, of utilising hydrogen might be to create synthetic fuels from it. So the idea here would be that we would capture CO2 from the atmosphere, so from the ambient atmosphere, and convert the hydrogen and CO2 to a range of synthetic fuels. I'll run through them later. So the pros here, that if we use atmospheric CO2, this is almost CO2 neutral. We can create some very nice behaving fuels. We can tailor our fuel process in the processes used here. We've been running Fischer-Tropsch processes for a long time, so we know how to do this. The downside is we haven't really yet got effective and cheap ways of collecting CO2 from the atmosphere. I do really mean the atmosphere here rather than, you know, the flue of a fossil fuel power plant. Because if you think about it, if say we were burning coal and we capture the CO2, if we then use that to create a synthetic fuel and burn that, the CO2 is eventually going to escape, right? So that is a net flux of CO2 to the atmosphere. So to make this a carbon neutral process, we have to capture that CO2 back from the air that we release to the air when we use a synthetic fuel. So we have to have a kind of round-trip neutral process. So the cons of this, you know, are going to be that high cost involved because there's lots of steps in the chain. You know, the general rule with new technologies is that the cost does, of course, decrease over time. I mean, if you compare the cost of solar and wind now to 10 years ago, you know, substantially cheaper. And so we should be exploring these things in the hope that actually technologically we can make them more efficient and improve costs over time. So, I mean, the other one other approach is to use renewable fuels that are not based on electricity production, but to use bio sources. And actually, I'm going to say a lot more about this later, but basically we can from bio sources generate fuels that look relatively similar to the ones we're used to burning. And depending on the source of the biomass, of course, if we're growing an annual cycle crop, for example, it's going to absorb CO2 back from the atmosphere through photosynthesis. So this should be a round-trip neutral CO2 process, but I'll show later why that's not always the case. So I won't dwell here because I'm going to go through this later, but you know, the pros of biomass are that we can create fuels with similar energy densities to the fossil fuels that we're used to. We're already blending ethanol into gasoline without any modifications, but there are limitations on that. And actually, biofuels can improve our emissions processes from combustion devices, which is also a benefit to air quality. I mean, the main downside of biofuels, of course, is the land use that we need to grow them. And so we cannot displace the whole of that fossil fuel demand with bioenergy because there just simply isn't the total resource to do that. And I suppose the problem, I think, with trying to vision what the future energy system will look like is it's going to be lots of different things, and we don't actually know, we don't have enough information to optimize how much biomass should we use, you know, how much hydrogen should we produce, how much should we be using heat pumps, how much should we be using hydrogen or electricity in industrial processes. We don't have that vision, and I'm a bit worried because we've only got, let's see, where are we at? We've only got 38 years to get to net zero globally. Okay, so we are in a bit of a rush. Or we should be. Okay. Okay, so I'm going to go through some of these options briefly and talk about pros and cons, I suppose, at a very surface level. Oh, well, we all like working on hydrogen right from a kinetics point of view because it's the simplest fuel we've got. We only need about 9 species and the chemistry is very simple. So that might be a reason for choosing hydrogen as your research topic compared to biofuels. So it's interesting. I found it interesting because I actually started to write these slides last year. And then when I was preparing to come here, I was like, actually, my view on this has changed even in the last 12 months. 12 months ago, I might have been a bit more evangelical about using hydrogen, not just in industrial heat sectors, but also in the domestic heating sector. And now I'm starting to think, well, no, can we actually produce enough energy to do that? Maybe not. So it can be part of our heat system, but probably not all. And as I say, in the UK, I don't know if the same is true in the US. Do you mainly use natural gas for heating your houses? Yeah? No? Oh, okay, so it's regional. Sorry? Oh, propane. Produced from... How is the propane produced? Right, but anyway, probably from fossil fuel sources, yeah. Okay, so some kind of fossil-derived gas is probably the main source of heat here in the US as well. And so this is a huge amount of energy demand to displace to low-carbon sources. So we've either got to transport more electricity to our houses if we're going to use heat pump technologies, or we've got to find a carbon-free or carbon-neutral gas. I mean, at the moment, we've got some tests going on in the UK where we're blending hydrogen up to 20% with natural gas in our gas system in certain parts of the UK. And actually, this is demonstrating that up to 20% by volume, we can do this without changing people's boilers or gas fires or cookers. The downside of this is that, if you actually calculate the CO2 savings, they're less than 10%, okay, because of the density differences between hydrogen and natural gas. So, it's a very sort of small saving, really, for the effort that it takes. So I kind of think we either need to go to full hydrogen or at least large hydrogen blends, or it's probably not worth the effort to do this. But the problem then is that hydrogen has quite different combustion properties from the natural gas. And so blending it to higher proportions starts to create problems. So shown already yesterday that we have much higher flame speeds and higher adiabatic flame temperatures, which will consequently affect thermal NOx production. Hydrogen has very wide flammability limits, but it has long ignition delay time, so it has a high octane number. In terms of material properties, it creates materials embrittlement, so we can't put it through the same steel pipelines that we have been using for natural gas. And in the UK, we are in the middle of a pipeline replacement process. And I don't know if that, I'm not sure if that was just happening anyway, or whether it's part of the potential there may be to switch to hydrogen. But we're replacing a lot of pipes with PTFE pipes, which should be hydrogen ready. And that's about halfway through for the UK. But that would have to be done. So obviously one of the things we're trying to mitigate as much as possible is hydrogen leakage, because it has low minimum ignition energy, it's highly flammable. So one of the other problems is that hydrogen is very light and diffusive, and so if we want to store it efficiently, then we will have to compress it at very high pressures or store it at temperatures well below zero. And there is an energy penalty, of course, in both of those storage methods. Issues that we might have to deal with in terms of combustion: it's odorless, but natural gas is really, we can just put some kind of sulfur compound in there if we're going to use it domestically. Premix flames, which we're used to using in natural gas boilers, for hydrogen, they have very low visibility. And so that's problematic because a user, a customer in a domestic setting needs to know whether there's a flame there, right? Because otherwise you've got issues that maybe be related to safety and someone burning themselves. So I showed the higher heating values of hydrogen and natural gas earlier in the week. So in terms of mass, hydrogen is pretty good, but in terms of storage, it's about a third of where natural gas is. So to satisfy the same energy demand, we need to transport 3 times as much, and that might affect the pressure that we deliver our gas, for example. But on the other hand, because of differences in density, we effectively get the same pressure drop for hydrogen and natural gas. And so actually that's a critical parameter in the pipeline network. So the same pipeline network, if upgraded to PTFE, could be used. Oh, I did include propane on here, so that's useful. Okay, so a few differences in terms of combustion and other properties. So, we've got a higher adiabatic flame temperature than both methane and propane. Hydrogen is substantially more diffusive. That might have benefits because if it does leak, it's going to diffuse very quickly and hopefully move us outside of the flammability limits, which are actually quite wide compared to other gases. In terms of mass, then, the heating value is favourable compared to other gases, but in terms of volume, it's not. It's less ignitable at low temperatures, so we've got higher RON. The minimum ignition temperature is similar, I guess, but the minimum ignition energy is much lower. Okay, so those are challenges that we have to deal with if we're going to use hydrogen in our network. So a quantity that's used quite a lot in burner and engineering is the Wobby Index, and it's a measure, well, it's designed to be a measure of the interchangeability of gases in gas burners. And so it's a ratio of the higher heating value of the fuel to the square root of the relative density compared to air. So D is a dimensionless number. And actually, what this is saying is that if fuels have a similar Wobby number, then all other things being equal, they should be interchangeable within our burner systems. And actually, hydrogen and natural gas are very similar. But the problem is that when we start to mix them, mixtures in between 100% of one or the other have quite different Wobby numbers. And so, we can, at the moment, we've decided we can test up to 20% hydrogen, and that's working, actually. But beyond that, we fall out of the range of Wobby indices that we can deal with in our current systems. And it's actually not until we get to sort of 90% and above hydrogen that we move back into the regime that we can use. So these intermediate mixtures, at least in the domestic supply system, are problematic. Okay, that I've shown you already, so I'll move on there. I suppose I'm sort of throwing in the question, how well can we model hydrogen? Because I'm sure that, well, probably all the people who are modeling hydrogen in CFD are in the other session. But I've talked a lot about the elementary reactions of hydrogen on Tuesday, I think. So we can do reasonably well, but there is a spread between models. There's probably been some models since this study was done, which is in 2010. So some models do better than others in terms of being able to predict the mass burning rate of hydrogen. The model that actually does the worst is actually the GRI Mech. I won't ask you to put your hands up if you're using GRI Mech. That's not a full criticism of GRI Mech, but it is 20 years old now. So we can do better than GRI Mech. And actually, probably some of the updates to reaction rate constants that I talked about on Tuesday would help to improve this further. So I think in terms of combustion, there are a few different challenges with using hydrogen in our systems. One is how to control for thermal NOx. So thermal NOx, of course, increases with temperature through the Zeldovich mechanism, which you may have come across before. And hydrogen has a higher adiabatic flame temperature than natural gas. But the advantage of burning hydrogen as a pure fuel is that we actually don't have to design around minimizing soot and CO, because there's no chance of them being formed. It's only when we look at mixtures that we've got a chance of unburnt hydrocarbons and soot and carbon monoxide. So hydrogen burners can't have a CO problem, in fact. There's no carbon in the fuel. And in fact, in terms of domestically, it's actually the main hazard from using natural gas is actually CO poisoning. So although, we might want to worry about leakage of hydrogen in our homes, it will actually reduce, if we do use it domestically, it will reduce issues related to people being asphyxiated by carbon monoxide. So what that means is that actually we don't have to worry about unburnt hydrocarbons in rich zones, for example, and we can start to think about cleverer designs to try and reduce the formation of thermal NOx. So, for example, we can burn rich, and then we can have air staging, or we could burn lean to try and reduce NOx that way. So we've got lots of different options without having to worry about CO quenching in our systems. That gets more difficult if we're trying to manage for the transition to hydrogen. So in the UK, there have been questions around whether or not now we can sell devices to people that are ready to burn hydrogen. So at the moment, we've all got natural gas coming into our houses. But can we sell someone a boiler that will currently work with natural gas, but if we do switch, will then the same boiler with minimal changes will work with hydrogen? That's more tricky because the natural gas system has to be able to control soot and CO and unburnt hydrocarbons, and also has to work with hydrogen. Okay, so again, you know, go to Twitter, the people will be rowing about this, saying people are being ripped off by being sold hydrogen-ready burners. Hydrogen's never coming. Yeah, let's not go there. So that's one issue. The second issue, for those of you that have been coming to the morning lectures here, you will have heard about quenching. So the quench distance is the largest characteristic distance that prevents the propagation of a flame. So if you have a current gas boiler, it's probably running pre-mixed, and what you'll find if you open it up is it's not a single burner, it's lots of small burners. Am I right? Does it look like that? Yeah. So the reason is because the burner diameter should be smaller than the quench distance for the fuel, okay, to stop your flame chasing back down and creating flashback. I thought I had a picture of flashback. I'll just, yeah. So this is a nicely behaved flame, but actually this is a flashback situation where the flame is chasing down the burner outlet. So that we want to avoid this. Well, the problem is that the quench distance for hydrogen, because it is so much more reactive, is substantially smaller than for natural gas. So for natural gas, for propane, etc., we're looking at maybe 1 millimetre at the very worst for DME, 2 millimetres for natural gas, for example. Okay, so that's already quite small as a burner size. But if we look to hydrogen, then we're an order of magnitude difference, so 0.2 millimetres or 0.2 to 0.3 millimetres. So if we think we can run a premixed burner device for hydrogen, then the burner size has to be smaller than 0.2 millimetres. It's quite difficult to engineer, in fact. I mean, one way around that, of course, is to not use a premixed system. So if we've got no oxygen coming through the burner pipe, then we should have a much lower incidence of flashback, but we might still get air entering into the burner. So we really do have to design for this small quench distance. So the two challenges here then are really to create small burner nozzles and to use diffusion rather than premixed flames, so non-aerated burners. Another challenge for hydrogen is flame visibility. I mean, actually, it's interesting to have conversations with people about this. I mean, what's people's view? Do people think that hydrogen flames are invisible? Anyone of that view? No. Because I showed a picture of a fire that we designed at Leeds chair, and he thought we added an additive actually to get the colour, which we hadn't. And I think one of the issues here is that actually premixed flames are far less visible than diffusion flames, and some debate about where the colour is coming from. My view is it's coming basically from emissions from water vapour. And actually, a lot of the emission is in the infrared part of the spectrum, which of course we can't see, but some of it does stray into the red and into the orange part of the electromagnetic spectrum. Diffusion flame, there is a paper actually by Schaefer et al. Suggesting a factor of 4 increase in emission intensity for diffusion hydrogen air flames compared to pre-mixed. So we've had some fun at Leeds trying to design a hydrogen fire. Whether it will ever come to market, whether we'll ever have hydrogen in homes, and I don't know, but we learned quite a lot of interesting things. So the general design principles are that this is a non-premixed burner setup to improve the flame visibility, which looks reasonably good, right? I mean, we got money from the government to do this project, and the premise was that, you know, we should be creating a fire that looks like the ones that people are used to having in their houses already. So, I mean, obviously in a natural gas fire, some of the emissions coming from soot. But now we're getting this more red flame because it's coming from the water vapor. We use impingement cooling, which is relatively easy in these fire designs because they've got like fake coals sitting on the top here to help us reduce NOx. But what we found was we can create a fire design that has extremely low NOx, much lower than the natural gas reference fire that we were comparing to. It wasn't very visible. It was visible in the dark, but not in daylight. So the argument that, you know, we shouldn't burn hydrogen because of the NOx isn't really true. We just have to redesign to prevent thermal NOx from forming. Very small burner nozzle size. Probably won't give you the details in case my colleague decides to patent that, but that was to avoid flashback. My frustration with this project was that the government was in a rush, and we were in the middle of COVID pandemic, so it wasn't a great situation, but they wanted a fire in a box, like it looks like in a shop, within 2 years of the start of the project. So we didn't really have time to do fundamental CFD to get an optimal design of the fire. So we were designing this really by trial and error, tweaking designs, burner sizes, coal arrangements, ignition igniters to try and get the best we could. But actually, I think, you know, a full optimization would give you a pretty good result. I mean, already we got a good result, but I think CFD would be very helpful in these circumstances. Okay, so going back to the issue about energy storage, if we decide, you know, that hydrogen is a nonsense in the domestic setting, which some people have decided already, then, okay, we're all going to need a heat pump, fine, I'll get one. But, you know, we're going to need to supply the electricity. So how are we going to store wind energy from windy days to winter calm days? Hydrogen is another option for doing that, right? So we can store it in salt caverns, etc. So that would then mean using hydrogen to dispatch electricity on those days where we don't have a primary supply. And that would be done through large power generators based on the gas turbine concept that we already use for natural gas. But we can't, for the reasons I've just kind of discussed, we can't just put hydrogen into the gas turbines that we currently use for natural gas. There will have to be a redesign of the injection systems and the combustors to give us a safe design without flashback, with stable flame and with low NOx. So there are challenges then for gas turbine operation on hydrogen, but there are some small hydrogen gas turbines already in operation. So it's perfectly feasible. We've just got to design out these potential hazards. So there is a joint venture between Mitsubishi and Hitachi that have designed a diffusion combustor. So again, it's not a premixed combustor, it's a diffusion flame-based combustor using low NOx technologies. And in this case, they're using steam injection to control for NOx. They can operate with very high percentages of hydrogen in the mix. So traditionally, NOx tends to be controlled in gas turbines using premixing. So we have a lean operation in the primary zone, reducing the temperature. So the switching to hydrogen, because of flashback issues, makes premixing very questionable. So we need to come up with new strategies for NOx reduction. And actually, steam injection is one suggestion of how we might do that, because steam reacts with the oxygen radical, suppressing the oxygen radical concentration, and that inhibits the thermal production of NOx through the Zeldovich mechanism. Actually, I added this to the slides since I sent them for printing. So I guess the PDF will be put online. I can send the updated version, but sure you all know the Zeldovich mechanism anyway. But so steam injection is one possible way that we can control for NOx in hydrogen devices. Well, hydrogen in aircraft, I don't know. Thierry seems to be a little bit worried about the safety aspects around that, but I think Airbus are throwing a lot of money at it, so there must be some possibility. But so the reality is really that to switch to hydrogen, we are going to need to redesign devices. We're going to need to design for low NOx. We're going to need to design safety mitigations for hydrogen leakage, and injection systems probably that won't be based on pre-mixed technologies that we currently use for natural gas. So I suppose on the upside, there's a lot of work to do for combustion scientists in the hydrogen area. I think one of the main issues is, how do we the starting point is to generate enough electricity to create hydrogen. I'm not really even going to say much about the steam reforming of fossil fuels to make hydrogen, because I actually don't think that's the way forward. But not everyone agrees with that. But until I see CCS operating at a very large scale, I haven't got a lot of faith in that as a method of hydrogen production. So let's move on now to ammonia. I've got to say, initially I was kind of scratching my head about, ammonia as part of a low-carbon combustion system, because I also work in atmospheric pollution and the dispersion of atmospheric pollutants, and ammonia is always put forward as one of the unsolved issues in air pollution. At the moment, it mainly comes from agriculture because of fertilization processes that we use that throw more nitrogen into the air than they do into the soil where we need it. So I was thinking, adding more ammonia to the atmosphere cannot be a very good plan. But again, it's one of those situations where we have to control for NOx from using ammonia, and we also have to control for ammonia emissions, so unburnt ammonia, so that ammonia doesn't increase in the atmosphere. So why are people even thinking about ammonia? It seems like an odd fuel, doesn't it? But the problem, as I mentioned earlier then, is that with hydrogen is that we will have to compress it in order to be able to store it and transport it easily. The other option is to either convert it to ammonia or to create ammonia directly, because ammonia only has to be compressed to just less than 10 atmospheres to be a liquid at room temperature, or we would have to cool it to just below 0. If you compare that to hydrogen, we'd have to compress it to over 100 atmospheres or cool it to below minus 250 degrees C to get liquid hydrogen that we could easily transport. So the reality is it's going to be easier to transport ammonia, and it's of higher energy density than hydrogen. So then the question is, could we use it as a direct fuel, or is it just a hydrogen carrier that we then might crack and reproduce the hydrogen that we would then use in our devices? One of the advantages of ammonia is that it physically it has similar properties to propane. That means that the storage and transport that we currently have for propane is likely to be also applicable to ammonia. The challenges for ammonia are that it has pretty low maximum burning velocity. It's not very ignitable. It doesn't burn very easily. And the main potential challenge from my point of view is that actually I don't want to see more ammonia going into the atmosphere. I mean, NOx, of course not, but neither ammonia. Because it contributes to particulate formation, and it's actually toxic. But, you know, there's a lot of enthusiastic people in the combustion area about ammonia, and it may well be that we can design processes that are effective. So one of the visions is then that we use our renewable power to generate hydrogen through electrolysis, and then we synthesize that with nitrogen to give us ammonia. I mean, we already have a process to do that, right? It's the Haber-Bosch process. The downside of that is it's quite expensive in terms of energy. But ignoring that for now, so then we can store and transport our ammonia easily, and then we can either burn it directly, or we can crack it to give us hydrogen that we can use in fuel cell vehicles, or we can use in hydrogen gas turbines, etc. This is a slide I've actually added. So the problem with the Haber-Bosch process, which converts from hydrogen and nitrogen to ammonia, is it requires high temperatures and pressures, and therefore it's an energy-intensive process. And we always should be mindful about this round-trip efficiency. You know, how much of the energy loss is at each chain of the conversion. But actually, there are some new developments. I'm not entirely sure how commercializable they are at the moment, but using fuel cell technology or reverse fuel cell to generate ammonia directly from electricity. And so this is potentially a way that we can store the energy, I suppose, that's in the hydrogen here without going through the energy-intensive Haber-Bosch process. So this is quite an efficient process, but the reaction is pretty slow. So that, you know, again, it's early stages, developments might happen. Okay, so going on then to the issue of emissions. So this is a simplification of ammonia pathways. Really what we're trying to do is take the lower pathway and avoid this passage through HNO to NO formation. Okay, so we're trying to minimize emissions of NOx, particularly NO, and also to minimize emissions of unburnt ammonia. Both of them, of course, contribute to atmospheric particulates and acidification. So the reactor conditions are going to strongly determine which of these chemical pathways we take, and therefore the selectivity of the products. So one of the issues might be that the increase of OH radicals in the lean region is going to impact on the production of HNO and potentially increase NOx. So again, we're looking for combustor designs. Ideas suggested in the literature include stratified injection or the use of mild combustion, so flameless combustion, to generate power from ammonia directly. Okay, so again, you know, to design those kind of devices probably includes reactor modeling where we need detailed chemistry and robust chemistry. So there's been quite a lot of work done recently to develop ammonia mechanisms. Not surprisingly, the people who have made most progress on this are people who were modelling NOx production from combustion processes for many years. So Peter Glaborg is of course, in that category. This is just one example of a model performance for a system that includes ammonia from Glaborg's group. And you can see a reasonable ability to predict nitrogen oxide, predict carbon monoxide, and to predict the consumption of ammonia from the model. I'll show perhaps a bit more of this study tomorrow. The Budapest group, so Thomas Charány's group in Budapest, have a series of pieces of work where they take an important fuel and they gather all the mechanisms from the literature and compare them to give us a consistent way of comparing how well the mechanisms are producing wide ranges of experimental data. And they have done that now for ammonia modeling, for ammonia models. So let's see, 2, 4, there's about eight models being compared here. So the prediction on the left here is of nitrous oxide. So the best model is that from Song et al. 2019, which does slightly better actually than the Glabor 2018 model, and actually also gives quite a good prediction of the ammonia consumption profile. Okay, so I'll talk a bit more about this kind of mechanism into comparison work tomorrow. Actually, yeah, one of the notes I've put here is just saying that basically this Song 2019 model actually comes from the Milan modeling group framework. So if you remember, I was talking about automatic mechanism generation and the MAMOX codes from Milan. So that has been the starting point, the Polimi mechanism for that Song ammonia scheme. So I don't know, yeah, probably got a few minutes just to start on the next section. So I guess as combustion scientists, we might be excited about turning electricity into liquid fuels so we can sort of utilize a lot of the knowledge and skills that we've developed for fossil fuels. And there are a lot of potential advantages of power to liquid fuels. And in some sectors, particularly aviation, they may end up being, the only feasible choice. It's a bit early days to say at the moment. So, big if, we have abundant renewable electricity. I mean, as I say, at the moment in the UK, we're sort of nudging into days where we have got hours at least of the year where we've got excess renewables. Then we can use those potentially to create hydrogen from electrolysis, and then we can turn that hydrogen with captured CO2 from the ambient air into a liquid fuel. Okay, so I reiterate the point that has to be CO2 captured from the ambient air if we're going to use these fuels in an atmospheric process with no CCS. So why bother? Why not just store the electricity or store the hydrogen? Well, basically, because, as I said at the beginning, liquids have quite nice properties. They have high energy densities in terms of volume and weight. They're well suited to the current infrastructures that we are addicted to already. And they can provide us with a means of long-term storage. So they may well have applications in difficult to decarbonise sectors. So, not the vehicle you're driving around the streets where you can drive a battery vehicle. I mean, I hold my hand up, I'm a combustion traitor. I have got an electric vehicle now, which is actually much nicer to drive than the horrible diesel I had before. So, but aviation, it's going to be a very difficult sector. Ammonia is not suitable for aviation because we can't carry all that nitrogen around. It's no use from an energy perspective. It's just adding weight that we can't afford to carry. So, and hydrogen may be possible for aviation applications, but there are clearly safety concerns there. Otherwise, we're stuck with using biofuels in aviation. Again, what's the overall resource? So power to liquid fuels may well have applications in aviation or in shipping or heavy goods. So the important thing then will be to make this process as efficient as possible. So obviously wind energy, not so much solar, but wind energy has become more and more efficient as turbines have got larger because they can access higher levels of wind resource above the atmospheric surface. Then we need to work on efficiency of electrolyzer processes for hydrogen production. Okay, the tricky part here really is the atmospheric capture of CO2. So we do have various designs for capturing CO2 from the atmosphere. It's much more difficult than it is from a power station stack, of course, because the concentrations are low. Well, here's a question for you, right? What is the global atmospheric average CO2 concentration right now? Sorry? Well, yes, more than 420 now, but good. I got lots of answers because I asked that to my students at Leeds, and you should have shouldn't everyone have a rough idea of where CO2 is? But if you compare that to CO2 in a power station plume, we're talking much lower concentrations, and so much more air has to be moved through the device in order to be able to capture the CO2, and that has an energy cost. So we do, I mean, I'm trying to think of, commercial CO2 capture. There's a system in Iceland, I think, which is operational. So there are operational systems, but a low number at this point in time. Okay, so that's probably the sticking point at the moment. And the overall cost, of course, of this process, well, sorry, go on to the next stage. The actual synthesization of the fuels is fairly straightforward, right? The Fischer-Tropsch process has been in commercial use for a very long time. So we know how to make the fuels once we've got hydrogen and CO2. But the cost of this is going to be driven by electricity prices. Because we need a lot of electricity to create the hydrogen, and we're going to need a lot of electricity to move enough air through our CO2 capture system to get the CO2. Okay, so this is overall a pretty poor efficiency round-trip process to store as power-to-liquid fuels. But it will still be worth doing if we can produce electricity cheap enough. And if not, we're just going to have to pay twice as much to fly from Leeds to Princeton. I guess that's the bottom line. Okay, so let's just take a break there. So we're kind of in a short section on power-to-liquid fuels, and here we're just thinking about the possible advantages and disadvantages, maybe relative to biomass-based fuels. So one of the advantages of power-to-liquid fuels are then that they have got high energy densities, both in terms of mass and in volume, and we do have huge renewable power potential. Now, how quickly we realise that and actually, generate renewable power using wind, solar is, I suppose, a different question. That's a political question, because we do have the technologies to easily do it, right? That's not necessarily a technical issue. Power-to-liquid fuels, we'll see in a minute, we can tailor them, and we can make nicely behaved fuels so that they will be lower in aromatics than traditional fuels, zero sulfur compared to traditional fuels, and we should be able to burn them fairly cleanly and drop them in to combustors that we already have. The main disadvantage is going to be the cost, because it's going to depend on electricity costs that will drive the cost of hydrogen production from electrolysis and direct capture of CO2 from air. And there are still a huge number of people that believe that CO2 capture from air is never going to happen. Right? So, there are a lot of diverse opinions in this field. So the cost and the overall round-trip efficiency are issues, because the overall efficiency is extremely low, probably less than 20%. And if you think about this in efficiency terms, it's questionable whether or not we might need more land than biofuels. But obviously in the UK, we're in a very good position, because most of our renewable power is going to come from offshore wind. So that has, I guess, a low land capability. The whole of the coastline of the UK, if you didn't know, is owned by the Queen. But actually, it turns out she does pay tax on money that she makes from it. So, because I was a bit like, hang on a minute, is she the person making all the money out of renewables? But actually, we do get some tax back from it. Sorry, that was a slight aside. Of course, we're going to get, you know, if we're burning liquid fuels that contain carbon, we're going to get pollutants, and at high temperatures, we're going to get NOx. But it's not going to be worse than fossil fuels we're using now. We can do better, actually. I guess one of the other main problems is this going to lock us into traditional engines, such that we're, you know, sluggish in developing other zero-emission innovations? Okay, I'm not mentioning any names, but I just had a coffee break conversation with someone who's addicted to flames and IC engines, and that's true of most people, right? I mean, even I haven't got rid of my gas fire. You know, people like existing ways of doing things. We're not going to develop power-to-liquid fuels rapidly enough to displace all fossil fuel use in the next 38 years. So there's a lot of people working on, I guess, sort of life cycle costs and life cycle environmental costs of producing various different alternative fuels. There's so many assumptions in these studies. It's, you know, you have to take them a little bit with a pinch of salt. So this is a projection to 2050 for a possible jet fuel that will come from this power-to-liquid process. So the reference is the current, the projected price of jet fuel from crude oil, and then comparing different routes via low temperature and high temperature electrolysis to power-to-liquid fuels via the methanol route and the Fischer-Tropsch route, which I'll briefly mention in a minute. I mean, obviously, the overall costs are lower if we get our CO2 from a concentrated CO2 source. But the problem there is, if we then are using the fuel in an aviation context, we're not going to capture the CO2 back. So I would just put a cross through this. I don't see how this is relevant, because that's not a carbon neutral process. Overall, there's not a massive difference between the methanol and the Fischer-Tropsch routes. We're looking at projections of twice the cost of the fossil fuel price. But, you know, if you'd followed the projected costs of wind energy over the last 15 years to now, the projected costs and the actual costs deviate massively. Projected costs for wind energy are much higher than they actually are now. So these projections, you know, they change very quickly. So there's two principal routes for power-to-liquid fuels, based on the assumption that we've generated our hydrogen and captured CO2. The first is the Fischer-Tropsch process, and the second is methanol synthesis and then conversion. And actually, like I say, we've been using the Fischer-Tropsch process for a very long time. This is well-established technology, and the fuel standards already allow for a 50% blend of Fischer-Tropsch synthetic fuel in a mixture. Power-to-liquid fuel via the methanol pathway is not yet approved, but I guess no anticipated problems in that area, really. So the Fischer-Tropsch process, the diagram here, I guess, of the overall process. So we've got our CO2 capture system here. So you'll see, I guess, diagrammatic figures of fans here, because that's just demonstrating the volume of air that we're going to need to draw through that CO2 capture device. Then we've got hydrogen from our electrolysis, going through Fischer-Tropsch synthesis, and then potentially upgrading if we want to reduce the oxygen content of the fuels. So that will depend on the application. There are limitations on the oxygen content, even in ground transportation fuels. But of course, for aviation applications, ideally we want the oxygen content to be low, because we want the energy content to weight to be as low as possible. So the CO2 is converted to CO via the inverse of the CO shift reaction, which is given here, or potentially using a high temperature electrolysis route might allow for the co-electrolysis of steam and CO2 directly producing H2 and CO in a single step. And one of the advantages of the Fischer-Tropsch process is that we can, by altering the CO to hydrogen ratio, we can design for different fuels. So process design can allow us to tailor the fuel to be as close as possible to a drop-in fuel that we might want to have. So the overall Fischer-Tropsch process can be described then as a combination of the Fischer-Tropsch reaction and the water-gas shift. These fuels then are going to most likely be straight-chain alkanes, and that gives us some advantages in terms of the combustion compared to current fossil fuels, which contain quite high aromatics. So, I mean, I don't know, anyone working in the field of catalysis? Oh, okay. Because I think actually there's a lot of scope in terms of alternative fuel generation for development of catalysis processes. So the Fischer-Tropsch process is a catalytic process. There's a range of possible catalysts that we can use. You know, we have a bit of a gap, really, of detailed heterogeneous reaction kinetics. Don't ask me any questions about this, because I don't know anything about it, really. And actually, I think it's something that we, as a community, have been very slow to pick up on. A lot of these processes are happening on catalyst surfaces, and there's a big gap in our ability to be able to model those. But if we could model them, then you know, we can potentially use our model to come up with an optimal reactor design and to give us product selectivity. So the main products are going to be linear alkanes, alkenes, and possibly alcohols, although we may want to upgrade to remove the oxygen from our system. So I've just given the overall pathway, possible pathways here. But, you know, obviously this is not gas phase kinetics. So physically what's happening is then we have the first step, which is the reactant absorption onto our catalyst surface. Then we have some kind of chain initiation happening at the surface, and then chain growth by CH2 insertion, which is why, you know, more likely we're going to end up with a linear alkane chain, and then chain termination, which is the abstraction of the hydrogen to give us an alkene, or addition of a CH3 species to form a paraffin, and then the product desorption. So to model this successfully, of course, we need to understand what's happening in terms of surface interactions. So the people who are involved in catalysis, do you do any modeling? Yeah, okay. So you're the sort of, that's the sort of skills that are needed to tailor these processes. I think I've just put one slide in on methanol synthesis. So again, it's a catalytic process for synthesizing methanol from CO2 and hydrogen. And I think there's a large range of catalysts probably under investigation for this process. I don't know an awful lot about the catalytic field, but my experience of it from colleagues who work in this field at Leeds is that it is a bit of a run some experiments with a given catalyst at a given sets of temperature and pressure conditions, and try another one. And it's quite a trial and error type design process, which I think would benefit really from more detailed modelling. So the yields from the process are highly dependent on the choice of catalyst, the process conditions, and you know, we're not very good at optimizing that. We were mainly using trial and error experiments. So once we've got these fuels, how do they behave under combustion? So the main features of a Fischer-Tropsch fuel are that we can tailor for high cetane numbers, which means, you know, they could be quite good diesel replacements. We've got low aromatic content in the fuel, and that will have an impact on soot, of course, and low sulfur, which is also advantageous. I mean, for the most part now in Europe and probably in the US, The sulfur content of diesel that's allowed is extremely small already. But sulfur does have a tendency to spoil catalysts that we might use in engine after treatments on combusting these fuels. And so a low sulfur content is advantageous from the point of view of other pollutant mitigation, like catalytic converters, diesel particle filters, etc. And if we want to, we can go through another process to upgrade removing the oxygen. So we've got several advantages here. The shorter ignition delay times that come from having a high cetane number facilitate lower pressures and temperatures, and that lowers the thermal NOx potential. We've got low tendency for catalyst poisoning because we've got low sulfur content. We've got low soot formation potential due to the lack of aromatics. But that aromatics in fossil fuels are there to, one of the reasons they're there is to improve lubrication, but we can add additives to fuels to do that if we want to. So low oxygen content of these fuels is more advantageous from an aviation perspective than some of the biomass fuels I'll go on to talk about in a moment because of the weight issue that we have for aviation. Okay, so overall we've got emission benefits compared to fossil fuels from synthetic fuels. Yeah, the problem is going to be the cost of producing them mainly. Okay, so I think this is just probably reiterating what I said on the last slide. The high cetane number then means we've got a short ignition delay time. So the fraction of fuel burnt under premix conditions is reduced, lowering the temperature and pressure gradients, and that lowers the production of thermal NOx. So there's been some experimental measurements comparing different gas to liquid, in this case, not, same fuels and just not turned power to liquid, for different percentage volumes, and you can see that as you increase the percentage of the GTL fraction, then we see small reductions in NOx. I'm not entirely sure if I'm going to show any NOx for biofuels, but we don't always see NOx reductions from blending biofuels like alcohols into diesel and gasoline. Sometimes we do see small NOx increases. So guaranteeing NOx reduction is a useful thing for synthetic fuels. There's no real reason why I put this diagram in. It's a nice, really nice diagram of how soot forms. So it's from the, I think from the symposium presentation from Hope Michelson. The symposium was in 2016. But it's just useful to see how particle processes happen in a flame in this case. But you can see that PAHs are a key part of that and lead to polymerization and particle inception, which gives us soot precursors that then will coagulate and grow and give us the soot aggregates that we're used to seeing from soot engines before abatement. So the fact that fuels have no aromatics or low aromatics will slow this process of soot formation down. I mean, perhaps it's a little bit surprising that the reductions aren't greater, but this is again looking at polyaromatic and total aromatic carbon content when we increase the GTL fraction from the same study from Wu et al. So we do see small reductions in soot from increasing the GTL fraction. I think perhaps I might have expected larger reductions, but no worse, I guess, is the point. Okay, so there is a huge number of alternative fuels, so I am whizzing through these. But if we move on now to biofuels, again, controversial topic really, mostly because the biofuels that we have generated over the last decade or two have come from first-generation feedstocks. So biofuels is an interesting topic because some people are vehemently against biofuels. But I think the problem is that you can't treat biofuels as a single entity, right? The range of feedstocks is huge. And the range of products that we can generate from those feedstocks is also huge. So there's no such thing as, biofuel. There are lots of different combinations, some of which we should be avoiding because they have pretty poor life cycle CO2 emissions, but some of which might be a useful source of energy. So we need to delineate rather than saying, biofuels are good or biofuels are bad. It really is a lot more complicated than that. So in terms of policies, we classify biofuels as different generations of feedstocks. So historically, most of our biofuels have come from first-generation feedstocks. And this is where some of the issues, I suppose, in terms of perception have come from, because these feedstocks, you can see from the list here, are all potential food sources. So corn, wheat, sugarcane, beet, that would go on to produce something like ethanol that we're blending into our gasoline, palm oil, rapeseed, soybean, sunflower, that will go on to be producing biodiesel. Okay, so our first-generation feedstocks will go on to produce first-generation fuels. Ethanol, I've put butanol because we're working on it, so I like it. But actually, commercially, butanol is not used hugely because of the low yields compared to ethanol. A biodiesel and hydrogenated vegetable oil. But the European Union has now decided that, quite rightly really, that we need to be moving more towards second-generation biofuels and moving away from biofuel feedstocks that could be impacting on food availability. So second-generation biofuels would be of two main source types, really. The first is waste products, which could come from food and agriculture. So, for example, corn stover, which is sort of left over from sweet corn. Bagasse is also a waste product. Used cooking oil is also a waste product. Forest residue, well, I could debate that for quite a long time, whether that's always a waste product or not, but we won't go there. But it potentially waste forest material from other industries like paper, timber for construction, etc. And then the second is dedicated energy crops. So something like miscanthus grass or willow coppice or jatropha are dedicated energy crops that potentially we can grow on fairly poor soils, so aren't necessarily competing with the type of land that we would use for food generation. Okay, and the second generation fuels that we might be aiming for would look similar. They're just much harder to generate from these second generation feedstocks. I mean, some of you might be working on other biofuels that you want to add to this list, and I'm not saying these are the only possible fuels, they're just examples. Third generation would be to come from algae sources, which can be generated industrially. Really, at the moment, the cost of that is too large, really, to be a likely source of fuels in the short term. So oils from algae are more likely to be used for products of much higher value than fuels, I would suggest. So the difficulties of moving to second generation feedstocks is that we've got basically these kind of woody biomasses, so lignocellulosic biomasses, rather than nice oils and things that we use from the first generation. So it's much harder to break down cell walls and things like this to generate usable sugars from second generation biomass. So at the moment, the yields from lignocellulosic biomass are likely to be lower. The cost is likely to be, well, let's just say it's going to be more difficult to compete in terms of cost. So the feedstocks are likely to be cheaper, but the processing is more difficult. So there's quite a lot of work going on into how we can generate useful intermediates from cellulose, hemicellulose, and lignin. Okay, so the useful intermediates might be, for example, butanol, levulinic acid, some of the furans, and the fuels. I've put some examples here that. I've not put the reference to that paper. That's not good. That came from the paper that I got this from. But again, well, there's lots of potentials. Could be alcohols. Furans are on the list, but I'm not going to dwell too much on those. I think there's too much toxicity potential from furans for them to be massively likely in terms of fuel usage. So there are lots of different options for second-generation biofuels, but we've got to come up with processes where we can improve the yields of production from those. And actually, I think I have got it on the slide, but the European Union is now mandating as we go forward higher percentages of these second-generation biofuels in fuel mixtures, so this has to happen. So other types of biofuels that we might be interested in looking at are the furans. Long-chain alcohols, I think the group from Archon and collaborators have been working on these. So octanol is an example. And, well, this is referring back, I suppose, to some of the things I was saying yesterday, that as we go to longer and longer chain alcohols, they behave more like the equivalent alkane. So octanol has a high cetane number, for example, compared to ethanol and butanol. We've got ethers, dimethyl ether, diethyl ether, and dibutyl ether. Levulinates, which is something that we're working on at Leeds with Trinity College Dublin, and blends of any of these that we might use to tailor fuel properties. I'll say more about that later. So at this stage, correct me if I'm wrong, but I think that really apart from DME, none of these are at the highest level of technology readiness, so commercially available. Okay, so ethanol from first-generation crops is produced via acid hydrolysis and sugar fermentation using enzymes and followed by distillation and dehydration. But the conversion of this lignocellulosic biomass is more difficult than hydrolysis of starch because you've got these polymers, these carbohydrate polymers, like cellulose and hemicellulose, and then you've got the remaining lignin. So none of these are soluble in water, and so we have to be clever about how we're going to create sugars from these starting compounds. So currently we're looking really at higher production costs. We either need to engineer new strains of enzymes to tackle these more difficult starting compounds, or we need to use other thermochemical methods. So pre-treatment of the biomass, for example, one possibility. Biobutanol, we show later, is in some senses it's a kind of a nicer fuel for blending than ethanol, has some favourable properties. So why are we not using it? I mean, there used to be a biobutanol plant in the UK, actually. I think it was in Hull, but it's no longer operational. And one of the problems with biobutanol is the lower yields compared to ethanol. So unfortunately, the enzyme strains that we used to create biobutanol were sensitive to the biobutanol concentration. And so when concentrations got above a certain value, then the enzymes died. And so it was difficult to get to high yields. So there is some work going on now in terms of genetically engineering E. coli strains that will be able to survive longer or to higher concentrations of butanol, and therefore to get higher efficiencies and higher overall yields this process. Theoretically, we can convert cellulose and hemicellulose to the furans. So going through hexoses and pentoses here. So I've actually added a couple of little diagrams of hemicellulose here and cellulose. So, of course, the furans are ring compounds, and although they might have very nice properties of fuels, I'll show a couple of slides on that later. In general, in the past, we've been worried about furans from the point of view of toxicity, both to humans and in environmental systems, so aquatic environments. And, you know, there are a lot of different rules related to fuels before you can put them into a fuel supply system for usage. Toxicity is obviously one of the criteria. And I mean, I don't know about formally, but informally, conversations with people who work in the oil and refinery industries are that they're not interested in anything that has a new concern over and above what they are dealing with fossil fuels right now. So if something is likely to be more toxic than gasoline or diesel, then it's not really going to progress too far. Well, I mean, we can produce furans, though, again, using acid hydrolysis at elevated temperatures. These things are hard to name when you've had a long day. Hydroxymethylfurfural, or HMF, and furfural can be produced, and then they can be further upgraded to produce biofuels like methylfuran and dimethylfuran. And at the moment, we can do that in the lab scale, but it's not something which is being done at the commercial scale. DME is something which can be produced at the commercial scale, and actually there are dedicated engines that have been designed to operate on DME. So DME can actually be also produced from lignocellulosic biomass, so it could be potential second-generation biofuel. So in this case, the biomass is gasified to produce syngas. So this is a high-temperature process which will break down cell walls, etc., to produce syngas. The syngas is converted to methanol by the process I showed you on the earlier slide. And then the methanol can be dehydrated to give us DME. DME can also be produced from wind-based electrolytic hydrogen and carbon dioxide, which was the process, the renewables process I mentioned earlier. And it's interesting to compare the life cycle greenhouse gases for those different production processes. So I'm just introducing now for the first time life cycle analysis. Has anyone ever been involved in doing that kind of analysis? No, we're all combustion scientists. But at the end of the day, this is an important component of trying to decide which of these pathways from, for example, renewable electricity or from biomass to alternative fuels. Because really we're trying to get the process that has the overall optimal costs, as well as overall savings in terms of greenhouse gas emissions, and potentially also overall the lowest air pollutant emissions, because we also need to improve air quality. So this was a study that was attempting to look at different routes to DME. So the first one is from CO2 and hydrogen. So that would be a kind of renewable energy route. The second was from bioprocesses. The third from natural gas. Actually, I can't remember what that one was. And then liquid natural gas is the last one. So if we look at the overall greenhouse gases, then, of course, the renewable electricity and the biomass routes are the lowest. And in fact, they also compete in terms of other overall emissions, so VOC, CO, NOx, etc. So, compared to the fossil routes, the environmental life cycle shows massive reductions from renewable sources. So I just want to say a bit more about the carbon footprint of fuels. Don't worry too much about the transportation distance for the fuel here, but we just want to look at the relative carbon footprint of various different options here. So the scale of this is greenhouse gas emissions in terms of CO2 equivalent per megajoule of fuel, or per megajoule of energy in the fuel. So CO2 equivalent is CO2 emissions plus any other greenhouse gas emissions kind of scaled on the CO2 scale. So that might be things like nitrous oxide, for example, or it might be methane, that have different global warming potentials from CO2. Okay, so for biofuels, nitrous oxide is a fairly key greenhouse gas because it comes from fertilization of crops. So I guess one of the things we don't want to do is to come up with a low CO2 fuel that's then going to create loads of nitrous oxide going into the atmosphere, because nitrous oxide has a massively higher global warming potential than CO2. Okay, so let's look at the rankings of the different fuels here. So maybe not surprisingly, really, that the lowest here is going to be hydrogen production from photovoltaic electrolysis. So it has a very low CO2 emission. And theoretically possible, but not happening in reality, I suppose, is H2 from natural gas, but with carbon capture and storage. So this is a steam reforming route. It's not as clean as electrolysis from green electricity. Then next up is when we convert the hydrogen to ammonia. Of course, there's a penalty in doing that, particularly if we use the Haber-Bosch process. So that has a higher greenhouse gas emission. And then we go up to methanol from biomass and DME from biomass here. So biomass life cycle emissions in this case look worse than using renewable energy. And then at the top, we've got methanol from natural gas, DME from natural gas, and even ammonia with CCS from natural gas is quite high. Okay, so this suggests really that from a life cycle point of view, hydrogen from renewable electricity is looking pretty good from a CO2 equivalent point of view. So what are the important properties then of potential biofuels? Well, they must meet the stipulated CO2 or CO2 equivalent, I should have said, reductions that are stated in the Renewable Energy Directive. So that's 50% reduction compared to the fossil fuel comparisons, reference, is what I was trying to say. The physical properties need to be suitable for blending at the moment. So as I say, we're already using 10% bioethanol in our gasoline, but we need to get much further than that if we're going to continue to use liquid fuels in transport. And we'll see a bit later on that there's a huge number of physical and chemical properties that we need to match in order to create drop-in fuels for blending. Viscosity, flash point, density, energy density, hygroscopy, etc., etc. I'll show some examples. They need to be non-toxic, or at least no more toxic than petrol and diesel. And they need to have appropriate chemical properties. So for diesel blending, of course, that means high cetane numbers. For gasoline blending, high octane numbers and high octane sensitivity. We need good heating values. We need low emissions of NOx, PM, unburnt hydrocarbons, CO, etc. And ideally, we need high yields from the biomass source, or at least the process needs to be cost competitive. And for second generation biofuels, that's currently challenging. So there's a lot to think about, actually, with biofuels. And there are, various hurdles that might trip us up in terms of being able to use these biofuels in reality. I do want to say a little bit just about carbon footprint. I mean, I'm not going to go over the process of life cycle assessment, but actually, I think it's good to be aware of where we are with this and where we're trying to head. This comes from a report from the Royal Academy of Engineering on the sustainability of liquid biofuels that was produced in 2017. And again, life cycle analysis is very dependent on the assumptions that are made in the analysis. So you'll see the error bars on the life cycle estimates are quite large, so bear that in mind. Okay, so what we're trying to estimate here is the carbon footprint in terms of CO2 equivalent per megajoule for our fuel, and compare that to, in this case, the petrol reference, and then where we're trying to get to in the European Union, at least, which is 50% reduction according to the Renewable Energy Directive requirements. Okay, we've got some box and whisker plots which are giving you an idea of the uncertainties in these estimates based on the assumptions made. Okay, so the cross will be the most likely estimate, but we've got some quite large error bars here. So if we look through the first generation biofuels, then we're looking here at bioethanol being produced from corn, from wheat, from sugarcane and sugar beet. And actually there's two columns here for each fuel. So the first one is ignoring the potential influence of land use change on greenhouse gas emissions. So that's saying, okay, we're not taking into account any potential. So for example, if we take over a forestry area and then we deforest it to create land for agriculture, there's a big impact of that land use change. And so it is really important that we should take into account that land use change. But unfortunately, when we do that, particularly for wheat, we're above current petrol and diesel. So we know where, even within the error bars, we're not going to reach the requirements of the Renewable Energy Directive. So you have to ignore land use change and its impacts to be able to do that. So ethanol from wheat, probably not really a very good plan going forward. The best feedstocks from first generation sources for ethanol are sugarcane and sugar beet. And actually here, even with land use change being included, at least within the error bars, they do meet the red. I guess the most likely estimate is above, but at least they are both below the petrol reference. Okay, so what's the reason for this? The reason, the likely reason is fertilization of the crops, potential yields, and of course, probable land use change, taking over land for biofuel generation. Well, I mean, I guess the opposite side of the story is we use a huge amount of land for meat production, probably more so than we do for biofuel production. So that's another potential saving for land if we decided to reduce our meat consumption. Let's look at biodiesel first generation. So the feedstocks are different here. They're oil-based, palm oil, rapeseed, soybean, sunflower. And again, if you take into account land use change, none of these even meet current diesel, let alone the Renewable Energy Directive requirements. Only really if you don't have an influence of land use change can you meet the RED directive with biodiesel. So if we move on to second generation then, this is obviously the reason why we are moving on to second generation. So we've got a range of potential fuels here, dedicated energy crops like short rotation coppice, miscanthus grass, switchgrass, and also agricultural waste from forest residue, corn stover, bagasse, etc. Actually, these have much lower life cycle CO2 emissions than first generation biofuels for two reasons. One, if something is a waste product, then from an accounting perspective, you don't have to count the embedded CO2 in it. So, because the accounting process will attribute the CO2 to the primary product, right? So this is a mathematical shift, which you can go home and ponder over whether that's fair or not. Sorry?
Why they don't do that with carbon capture?
What do you mean? Okay, I think I answered that question earlier. So the question was, why don't we capture CO2 from a power plant and use it to generate fuel? It's not really related to biomass, the question, but my answer to that question earlier was that round-trip process is not carbon neutral. It just gives you twice as much utilization for the CO2 that you produce, but it doesn't give you a carbon neutral process, right? Because eventually you'll use the fuel and the CO2 will go back to the atmosphere. So the point of utilizing biomass sources is that the biomass will absorb CO2 from the atmosphere in photosynthesis. Well, since we're talking generally in debate, I mean, the UK is actually the biggest importer of biomass resources for power generation in the world, right? It's Yorkshire. It's in Yorkshire. We have this massive power station, Drax. It's a 4-gigawatt power station. Southern regions of the United States ship us trees and we burn them to generate electricity. And they're classified as forest residues. And so actually Drax Power Station gets a lot of subsidies from the UK government. Now, how long those trees take to regrow is an interesting question, right? Which is why, I guess in the second generation biofuels, we don't have primary forest here because it might take 10 years or 20 years to reabsorb that CO2. So we have what are considered to be short rotation crops. So a coppice, miscanthus, switchgrass should reabsorb that CO2 within a yearly cycle. And that's the kind of timescales we need to be operating on. Okay, so it's all about really how that CO2 is going to be reabsorbed from the atmosphere. So in terms of second generation bioethanol, from a life cycle point of view, most of these, some of it might be an accounting trick, but most of these feedstocks meet, or at least meet, the requirements of the RED directive for 50% reduction compared to gasoline. Okay, so there's some, I guess, some optimism around second generation sources. The difficulty, as I said, is actually, the production processes from these trickier lignocellulosic feedstocks. This is an interesting plot. So this is biodiesel from third generation, so from algal sources. So really all you need to get from this is the size of the error bar. It's quite large, and so algae might be a great thing, or it might be a terrible thing. And according to current estimates, we don't really know. So, I mean, I would suggest, is algae, I'm not saying anyone shouldn't be working on algae, but probably in the timescales of 2050, I'm not entirely sure whether it's going to be that helpful. I'm going to past, aren't I, for the next break, am I? 15:15. Are you sure? 15:15. Oh, okay. Oh, sure. Let's look now at some fuel properties. So I don't know, we're combustion scientists, and it's only recently that I started thinking a little bit outside the box. We thought, oh, we can calculate cetane number, or measure cetane number, or octane number, or ignition delays. And then we actually started to think about generating a drop in fuel and went, oh, actually, there's a massive list of things that we need to match in order to be able to do that, unless the regulations are going to change. So, I mean, this list has got an etc. on the bottom, so it's not even the whole list. So some of this data came from a paper by Tomlin et al., which I think is the Archon group. They are starting to construct a database of these properties for potential fuels, which I think would be a very useful step forward. Okay, so chemically we're interested in the ignition delay time, but there's no standard related to that. The standards are related to cetane number for diesel. This is the European number, the US one is lower. The research octane number and the motor octane number, which are for gasoline blends. I mean, I haven't put the US standard here. This is a Eurocentric plot. So Euro 6 standards for emissions from the vehicle. Was an interesting question. Where does the UK now stand in relation to these European standards? I don't even know the answer. But, you know, we're buying vehicles made in Europe, so presumably they still meet Euro 6. We've got standards on viscosity at 40 degrees C. We've got standards on density. We've got standards on cloud point temperature, which is the temperature where precipitates will start to form in our fuel. We've got standards on lubricity. We've got standards on corrosion, on oxygen content, etc., etc. So if we're trying to generate a drop in fuel from biomass sources, we have actually got to think about all these things. So just as a simple property comparison, just comparing ethanol with isobutanol here. They've got quite different vapor pressures. They've got different octane numbers. So ethanol is better at resisting knock than isobutanol, but the energy content in terms of a percentage of gasoline is pretty low for ethanol. So when we went from 5 to 10% ethanol in our fuel, it wasn't that long ago, a few months ago, there's a lot of complaints in the press about people exaggerating about how they had to fill up their tanks more often because the energy content is less. Actually, butanol is favourable in that sense. And the oxygen content of butanol is lower. So that would be useful in terms of the blending walls, because at the moment, we can't, in the UK, I don't know what the US situation is, but we can't get above 10% ethanol, because that takes us to the limit for the oxygen content of 3.5%. But that would actually be equivalent to, the same would be equivalent for 16% isobutanol blend, which I think is the US limit for butanol in fuels. So we can put more renewable, if we can generate second generation isobutanol, we can put more of it into our tank currently than we would be able to do for ethanol. There's a comparison slide here for the Furans with a RON 95 E10 gasoline, which is what we have standardly in the pumps now. What did I want to say here? So the lower heating value for the Furans is actually more similar to the gasoline than ethanol. Depending on the choice, you've either got higher or lower octane numbers. So from a combustion perspective, the Furans look quite good, but maybe from a toxicity perspective, they don't. So I mentioned flashpoint yesterday. So gasoline's very volatile already, and so in the fuel tank, the vapor's too rich to be flammable. So adding ethanol or butanol or any of these other drop-in fuels to the blend is going to change the lean and rich limits, and also going to change the overall flash point of the blend. So, but we still have to meet the flash point well, not for gasoline actually, but for diesel we still have to meet the flashpoint limits. Well, the worry for gasoline is that actually we will move back into to a leaner situation where we're within the flammability limits for the fuel blend. So typically then, gasoline's not going to form a flammable mixture until the ambient temperature is below minus 20 degrees C, which is the rich limit. But when we add ethanol, the higher flash point and the different stoichiometry is going to make a potential explosion more likely at ambient temperatures. There has been some measurements done in Sweden which has shown that E85, so that's 15%, so that's 85% ethanol, has a flammable mixture at commonly found atmospheric conditions of 2 to 5 degrees and down to minus 18. So longer carbon chains are going to increase the flash point. And that makes them more suitable for, so ethanol is not really suitable in that respect for blending with diesel, but the longer carbon chain alcohols like octanol, for example, are likely to be more suitable for diesel blending. So, some flashpoint examples then of given fuels. So for gasoline, flashpoint is extremely low, well below 0. But for ethanol, the flashpoint is around atmospheric conditions, 16 degrees. So blending ethanol into gasoline will increase the flashpoint. Diesel has to be greater than 52 for the standard. Biodiesel has a much higher flash point actually, and that might be useful for blending. If we look at ethanol then, if we blend ethanol with diesel, it will drop us below the legal limit for the flash point. If we blend it with biodiesel and diesel, then maybe we can solve that problem. Butanol is more suitable from the point of view of blending with diesel because it has a higher flash point than ethanol. So it's going to give a lower reduction in our flash point. We might remain within the limits. But as we go up to longer carbon chains, so we only have to get to pentanol really to get to values of the flash point which are similar to diesel. So anything from pentanol upwards in terms of carbon length would be suitable from this perspective for a diesel blend. Yeah, so I think then we're at the next break. I hope I'm going to get to the end and the extra bit I want to show. Anyway, okay, coffee time. Okay, so we better go back to some combustion. Since we had a little break for combustion earlier. So, some of this will be, I think, probably a revision of one or two things I said yesterday. And then whatever happens, I want to show you a case study from some work that we've been doing on trying to generate a mechanism for a biofuel blend. It's kind of partway through that process, but using automatic mechanism generation tools that I talked about yesterday, was it? So whether I'll get through the rest of the other slides, I don't know, but we'll see. Okay, so this is probably, along the lines of what I was trying to say yesterday, that we, over time, we've developed our idea about fuel mechanisms from, mainly from alkanes, really from non-oxygenated hydrocarbons. But many biofuels contain oxygen, and they have different functional groups to the species for which we've developed a lot of our tools. So oxygen bonds, carbon-carbon double bonds, etc. But we know if we want to develop models to help us understand how these fuels will behave, then we might need to develop new mechanistic pathways. So there's a really great review actually from Charlie Westbrook that came out last. What have I done now? Oh, okay. Basically, they're designed for men in suits, aren't they? Yeah, there's a really great review from Charlie Westbrook talking about mechanistic development for biofuels, and he's one of the people who has the most experience of mechanism development and combustion, so it's worth a read. The main take-home points from his review are that we develop key reaction pathways based on experience from well-known fuels, maybe from bond energies. Then, at the next stage, we might be populating our rate constants using estimates. So based on, functional groups or analogies with other similar compounds. And then we need, well, I don't know if I would agree with him on this, but the suggestion is that we then have to do some fundamental experiments to test our mechanism that we've developed and potentially help us to understand better whether our estimated rate constants are in the right ballpark or correct. Carry out some sensitivity analysis to identify the reactions or parameters that are leading to the largest uncertainties in our predictions, and then go away and do more detailed kinetics or perform theory calculations for those fuel-specific reactions, and then kind of iterate until some consensus emerges. But, time's ticking in terms of climate solutions, and so we haven't got 20 years to develop a new mechanism for a new fuel. We want to try and do this within a reasonable timescale. So I'll just go through a few examples on the influence of functional groups in biofuels, and then I'll show you this case study and the use of RMG. I mean, I did talk about this yesterday, really, so just to reiterate the point that basically for alcohols, if we've got a short-chain alcohol, then there's a much stronger influence of the OH group on the alcohol, and that will tend to retard low-temperature chemistry and make those short-chain alcohols more suitable for blending with gasoline-type fuels, where we want high octane numbers and NOx suppression. So, for ethanol, across the range, we've got longer ignition delays than we do for gasoline. For the butanols, I think I showed that, from most of the temperature range, for an N-butanol, we've got longer ignition delays. And for isobutanol, I'll show later, we have got longer ignition delays over the whole range. But then when we start to go to the longer chain alcohols, then the influence of the neighbouring OH group is less, and these start to behave more like alkanes. So C5 and higher are going to have lower octane numbers, but higher cetane numbers, and so these are more suitable for diesel blending. So I just put in here an example of a suggested long-chain alcohol that's got a high cetane number and therefore might be more suitable for diesel blending. So it's part of the tailor-made fuels from Biomass program, which is, I think, led by Heinz Pitch, anyway, wherever Heinz Pitch is. And then there's another group working on octanol production process via acetone and furfural from Biomass. So this is a synthesis process involving the furans, but actually a conversion process that's giving us basically a straight chain alcohol. And that will have physical and combustion properties that are more similar to diesel. I don't know if I showed exactly this diagram yesterday, but it's linked to the diagram I showed yesterday. So basically, as the alcohol chain gets longer, then the alkane-like part of it increases in influence. And so when we get to octanol, we've got basically highest cetane number of all these alcohols here. So as we increase the chain length, the cetane number will increase, and the RON and the MON will decrease. Okay, so what that suggests is, at least from a combustion perspective, that the short-chain alcohols are more suitable for gasoline blending and the long-chain alcohols are more suitable for diesel blending. Oh, I've got a typo alert here, actually. I think in the notes it says decreases, but it should say increases, which is why I've put it in red. So this is, I think, some work by Argonne National Labs looking at the influence of ethanol on ignition delays compared to phase gasoline and other surrogates. And you can see there is some surrogate dependency on the influence of ethanol, but in general, for most of the temperature range, increasing the ethanol from 10 to 30% leads to longer ignition delay times. But interestingly, like the N-butanol plot that I showed yesterday, there actually is a crossover here. So actually, at higher temperatures, there is a small region where increasing the ethanol, hang on a minute, which is which? Yeah, so there is, wait a minute, which is which here, sorry. So yeah, the lowest ethanol blend here has the longest ignition delay time, and the highest ethanol blend has a shorter ignition delay time. Okay, so we saw that with butanol. The crossover temperature is slightly different, but there is a temperature dependency on the ability of these fuels to suppress NOx. And the reason for that really is that the underlying gasoline has this NTC region. And so there is a region where there is an influence of that. This is a similar example from N-butanol. I showed some of this data yesterday. Let's just ignore the complicated sensitivity analysis for now. The gasoline or the gasoline and gasoline surrogate has this weak NTC, whereas the N-butanol, it doesn't have quite Arrhenius behavior, but it's got more Arrhenius-like behavior. At the lower temperature region, it's actually giving a lengthening of the ignition delay time. So it's slowing down the low temperature heat release and slowing down the ignition delay. But then the crossover temperature here is slightly lower than the ethanol plot that I showed. But at the higher temperatures, the N-butanol is actually increasing the reactivity and so shortening the ignition delay. And it's because gasoline is going through this region of negative temperature coefficient where you increase the temperature and actually the fuel-air mixture becomes less reactive. Okay, so there is an interaction between the NTC and the influence of the alcohol that we're blending. I won't dwell on this plot, it's not too easy to interpret, but basically, well, the story is actually when we submitted the paper showing that, where the referees didn't quite believe as it was real and suggested it was some facility effect from the RCM. But actually, we actually did some spark ignition engine tests as well, and we saw that same type of crossover behavior. So I am reasonably confident that it's not an experimental quirk, that actually is a real effect. But actually, when we went on to look at isobutanol, the effect is less pronounced. So at high temperatures, all of the isobutanol blends, so we're looking all the way up to 70%, and then pure isobutanol here, lead to longer ignition delay times. But at low temperatures, IB5 and IB10 are actually more reactive. And so again, the anti-NOx qualities are going to depend on the incident temperatures. So I think what it suggests is that actually it kind of reiterates the point I made yesterday that just using octane numbers for fuels, it's a useful first guideline, but there is a real temperature dependency of the effects of blending, which we can understand much better by looking at the whole temperature range. I mean, another thing that, of course, we're concerned about, and of course the purchasers of fuel are going to be concerned about, is whether or not we're actually going to lose any power from blending these fuels into our engine. So we've already said that basically ethanol has a lower energy content, so you're going to get slightly less miles per gallon from blending more ethanol. But how will it affect engine performance? And actually that is related to where the NOx boundaries are for the fuel. So we looked at quite a number of different blends of isobutanol with gasoline, and basically in general the isobutanol blending delays the NOx onset, and actually above 20% we don't see any NOx in the engine, and all the blends decrease the NOx intensity. The problem is if we don't change anything, then the higher butanol blends give us a drop in the indicated power. So the gasoline surrogate is the black line here. So the peak power is, let's see, so around 7.2 for the gasoline. And then as we add more butanol, that peak drops. And the spark timing where the peak occurs actually shifts. So we could, by shifting the spark advance, actually recover the same power, even at 50% butanol blends. When we get to 70%, then there is no opportunity to do that. So the fact that the fuel is not resistant allows us to change the spark timing to recover the indicative power back. And so that's actually quite a useful property. And actually, I don't know if I fully understand this, but that was more possible for the 50% blend than it was for the 30%. And then maybe more intuitively we would expect if we get to higher butanol blends, then the power has actually decreased by quite a number of percent. But this suggests that basically we could get to 50% without losing power from the engine. Okay, I will go back to talk about a bit of kinetics now. So it's building on what I said yesterday. So the issue the interesting thing maybe about the biofuels is that we have this influence of the different functional groups that we get. So I've probably mentioned many times now that in general low temperature oxidation pathways depend on forming the peroxy radical from the initial alkyl, and then the isomerization of that to hydroperoxy alkyl radical, second oxygen addition, etc. So from the initial hydrogen abstraction by OH, we form two OHs back, and that's the low temperature pathway. So the different functional groups that we have on biofuels potentially are going to influence how effective that low temperature oxidation pathway is. And actually there's another useful review paper here from Brandon Rotavera and Craig Tatjas, came out last year, trying to summarize the effects of these different functional groups. And so if we look at the various different effects that can happen because of the influence of functional groups that we see in biofuels, the first is that the ketohydroperoxide can dissociate to give two stable products and not OH. And what that means is instead of having a chain branching process, we've got a chain propagation process. Okay, so that's going to slow down the low temperature chemistry. I showed yesterday some examples of the influence of bond energies in groups that are neighboring to the OH and an alcohol, for example, and that affects the selectivity of the radical that we form by that initial hydrogen extraction. So I think I showed an example for butanol yesterday, where we know that the hydrogen abstraction from the alpha site is favored, and that leads to a higher probability that the reactions will go to termination rather than chain branching. And the other effect, which I didn't mention yesterday, is stabilization of the RO2 radical, and that will change how much of the RO2 goes to QOH, and then the subsequent second oxygen addition isomerization pathways that lead to chain branching. Okay, so all of these effects are possible. And so there's a nice summary diagram in the review paper, which is showing the possible influence of functional groups at different stages of that low temperature pathway. So in terms of the functional groups I'm talking about, yesterday we mentioned the alcohol, which is the OH group. We might have an ester, which has a double bond oxygen and a single bond oxygen, or a ketone, which is a carbon double bond oxygen, or an ether, which is single bond oxygen, or furans, which have a 5-membered ring. And so from the point of view of using the reaction mechanism generators, these are all challenges to techniques that were initially developed for alkanes and maybe alkenes. So if we think about the influence of these possible differences in functional groups, then to start with, then we've got changes to the initial site of hydrogen abstraction. So the alpha site being favoured for an alcohol, for example. Then we've got potential changes to the relative stability of RO2 and QOH. So that might change the equilibrium constant for that isomerization pathway. The QOH might dissociate differently rather than going through this second oxygen addition. The thermochemistry for that oxygen addition might be different. We might have modified isomerization pathways, and then we've got potentially alternative dissociation pathways for the ketohydroperoxide. So we've got a lot of different possibilities for for the different chemical structures of the biofuels to impact on the low temperature chemistry. Acknowledgements to Brandon for giving me this nice animated slide. By the way, it's worth pointing out that Brandon actually did contribute one of the webinars on this topic. You're all watching them. You should all be watching some of them, at least. So during the pandemic, the Combustion Institute started a webinar series to try and keep everyone connected. And there's quite a few useful ones, but Brandon gave one. I think I mentioned Mike Burke's as well. So these are worth looking up. There's a YouTube channel where you can find those. In this nice slide that Brandon gave to me, he's comparing basically the oxygenated fuel compared to, or in this case, alkane equivalent, and showing what the difference would be. So for the first one, we're comparing 1-butanol and butanol with N-butane. And as I've already shown them, basically, that N-butane has this NTC region, whereas we don't see that in the butanol. The second one is a comparison between N-pentane and methyl hexanoate. So here, the oxygenated fuel still shows an NTC actually, but it's shifted relative to the alkane. These are the pentanones in relation to N-pentane. So here we'll actually see the creation of an NTC and also the lengthening of ignition delays at low temperatures. This is dimethyl ether compared to propane. So we've got the additional oxygen here. So dimethyl ether is far more reactive than propane, so we get much shorter ignition delays. Tetrahydrofuran compared to cyclopentane. So again, we see an increase in the reactivity from the addition of the oxygen group. And 2-methyl tetrahydrofuran compared to toluene. So again, the furans are more reactive and so have shorter ignition delay times. So these changes to the functional groups in the molecule do create challenges for mechanism validation. Can't read that from there. So fuels are more complex than the surrogates that we use for gasoline and diesel in some ways. And the mechanisms that we're creating to describe these biofuels are quite large, so that's a lot of reactions to populate using fundamental kinetics. So this is not going to happen really in a finite time. So we are going to have to use some of the methods that I talked about earlier in the week to populate this data. So group additivity for thermochemistry, for example, and functional groups and rate rules for the different reaction classes. So I'll go on now to change files and just show you the case study for the example that we've looked at, because it's quite interesting just to have tried this within an automatic mechanism generator and to see the problems that we ran into and how we solved them. Well, not we, Christian, the postdoc, solved them. Okay, it's just, okay. Okay, so these slides were mostly put together by Christian Mickelbach, who's a postdoc in the group at Leeds. So this is part of an overall project that we're actually doing in collaboration with Stephen Dooley's group at Trinity College Dublin. So overall, the project is a kind of end-to-end. So the group at Trinity and one of my colleagues at Leeds are working on production of these biofuel blends from second-generation feedstocks. And another colleague at Leeds is leading the life cycle analysis of the fuel production and utilisation processes. And we're working on a combustion and also utilisation in engines and emission measurements. So it incorporates, it's a kind of, I guess it's a very, very small version of Co-Optima, but just, you know, nowhere near as much money involved. Eventually, we want to start with ethanol and butanol as starting fuels, and we're going to be using those to try and upgrade to tailored fuel blends from second-generation feedstocks. So we're starting with the kind of ethyl version, and we want to then move on to the butanol equivalent. So we are producing mixtures of an ethyl levulinate, ethanol, and diethyl ether from at the moment from corn stover. And so then we're trying to develop a model that will allow us to predict the combustion properties. And the idea then is so there is actually already a model in the literature for these fuel blends. But there is nothing really for the butanol version. And as far as I'm aware, but I would like to be corrected on this, for butyl levulinate, I don't think there's anything in the literature and there's very little data. So we're kind of starting from scratch. But it's been quite interesting because here we have all the functional groups I've just been talking about in terms of their influence, potential influence on the combustion. Okay, so well, ethanol, okay, there's lots of mechanisms in the literature. And probably, well, in fact, what we discovered was that RMG, which is the reaction mechanism generation software that we're using, does have a reasonably good representation of the alcohol group. But we've also got diethyl ether, and then the ethyl levulinate is more complex because it has two double bonds to oxygen as well as single bond to oxygen. So we've got ester groups here that we found were not that well represented within RMG. So the idea was that we want to develop a way of producing this blended mechanism in RNG that we can then translate to the butanolic version. So ideally what we wanted to do was start with nothing and just ask RMG to do it. To do that, we basically just put into RMG, well, we always have a base mechanism, which I'm pretty sure is the Aramco scheme in RMG. And then we basically just put in our fuel molecule and several of the early radicals in that low temperature branching chain, so just as Smiles' descriptions. And then we just ran it to see what happened. And so this is recent data on the ignition delay times from Isaev et al. And so you can see that the reaction mechanism generation code, without any sort of seeding in terms of prompting it of reaction classes that we might expect, does a really bad job. So this is a bit disappointing, to be honest, because that means that basically we can't do the same for butanol. It's not able to find the low temperature pathways without any hints. So there are several problems, basically. There are gaps in the database for the functional groups, really, that we were interested in. And also, it doesn't seem like it's going to be possible to make this happen without any kind of seeding of the scheme. So in RMG, what you can do is you can give it a seed mechanism which at least contains some of the reactions that you're interested in, or you think might be in the combustion reaction chain, and then it will go and look for further pathways and kind of complete the job for you. So the seedless attempt at doing this basically just doesn't give us any low temperature chemistry. So that was a sort of failed first step. So what we then did was to add a seed mechanism, at least for diethyl ether, which came from Tranital in 2019. At least this includes, initiation, chain branching reactions, and RMG does a reasonably good job of then filling in the rest. Okay, so this was quite a big improvement over the seedless mechanism, the blue, but it's still not reactive enough compared to the experimental data. And also, what's I guess concerning about this is that we don't have the we don't have equivalent seed mechanisms for the butyl levulinate, for example. So we're going to have to make them. So then, well, obviously there was massive scope for further improvement, and so even with the seeded mechanism, there was still scope for improvement. And what Christine discovered was that the RMG database was quite lacking in training reactions for the groups that are specific to our oxygenated species. So the alcohol group for ethanol was fairly well represented, but the ethers, esters, ketones needed a database update for a lot of the reaction families that we want to include. So hydrogen abstraction is an obvious one for the start of the low temperature sequence. So hydrogen migration, cyclic ether formation, radical recombination. So RMG will allow you to add information if you have got training data, for example, for reaction classes, or training data for that will relate to thermodynamic information. So it's got the tools to do this. It's just, quite a tedious effort. So this is Christian's work, not mine. So I'm just finding it interesting, and he's putting all the effort in. I'll show you an example on the next slide. But what we found was that after making these database updates for oxygenated species, then the simulations are significantly improved and are now quite a reasonable representation of the experimental data. So just to give you an example, so in terms of database training, we can kind of split our levulinate into two different functional groups, so into a ketone and an ester functional group. And then we can look in the literature to say, well, okay, we're not going to find information directly for ethyl levulinate, but we might find other species for which there is quite high quality data for these functional groups. And in fact, for the ketone group, the methyl ethyl ketone can be used as training to represent this particular group. And for this compound, that has been some very high level theory calculations performed. And so we can present that data to RNG to allow it to use it as training data in the mechanism generation process. Christian also needed to add some new group structures to RMG. Oh, okay, well, he wrote this slide. He's saying this is tedious. You have to do it by hand because you have to describe all the adjacencies of the molecule structure. And you have to be, I think he's basically saying he made a mistake in the first time he did this because he's saying beware of human error in getting these adjacency groups correct. Let me go back to the previous slide. Point being that once we added this new training data that related to the functional groups that we've got and updated the group structures to allow group additivity to be used correctly, then we got a massive improvement in the mechanism. The other suggestion here is that to do some common sense checks along the way. So this involves basically carrying out sensitivity analysis for a start. So, you know, if you're not getting good predictions, do a sensitivity analysis for the predicted ignition delays, because what we found was that there were some really curious reactions that cropped up that we knew couldn't be right, that just had weird estimates for the data. And actually just removing those reactions just gave us a massive improvement in the predictions. So there was, you know, just some crazy suggestions came out. But actually, well, one of the interesting things was that RMG actually does a common sense check based on just limit values just from simple collision theory. So this goes back, I think, to Monday or Tuesday's lectures, and calculates a collision rate violator for all the reaction rate constants in the scheme. And actually, Christian, when he ran this, found collision rate violation factors of 21 orders of magnitude. And so he, for a few weeks, he was pretty frustrated and saying, oh, I can't get enough memory to run RMG, and it's never converging, and blah, blah, blah. And actually, the reason was because there was some estimated rates in the seed mechanism that were estimated for certain ranges of temperature. And when you're running RMG outside of those reaction rate constants were, you know, orders of magnitude away from common sense limit values. And so this is really something worth doing in RMG if you're getting stuck. That goes back, I think, to, I mentioned Hai Wang's paper, which is the person who developed this approach, and found that, you know, in pretty much all the mechanisms he looked at, there were reactions that were violating these collision rate estimate limits. So that was kind of interesting. Okay, so having gone through all of this, it's taken quite a long time, I've got to say. I'm glad it wasn't me that was doing it. But if you do a careful job, then actually we found that, you know, you can get pretty sensible mechanism out of RMG. And so now we're just basically gathering data to do validation comparisons. So we've got ignition delay times for the component fuels, for diethyl ether, for ethyl levulinate. We've got species data for ethyl levulinate from a jet stirred reactor. We're doing quite a good job of simulating this. Actually, ignition delay times for at least the bimixture of diethyl ether and ethanol. And compared to the seed mechanism that we used, which was the tram mechanism, if you remember, we are doing much better from having applied RMG than the original seed mechanism that we started with, including all the updates that we've made. So I guess the conclusion is that it's been quite laborious, although it will be quicker next time. We've now got the experience, but the model now can be extrapolated beyond the regime that the seed mechanism was, I guess, at least partially tuned, probably. And so I think we're reasonably confident in the mechanism that we've got. Not exactly sure where we're going to go with the butanol version of this, because we will have to estimate some rate constants to get a seed mechanism there. So what do we learn? You know, mechanism generation is not a black box. Most of these things are not, right? You do actually need some expertise to apply these. So there was, some careful human interaction involved. But actually, the generator does provide some tools for you to help you with those common sense checks. And sensitivity analysis, which is, local sensitivity analysis freely available in Chemkin, also provides you with some tools to do that. Disappointingly, I think, it took a reasonable seed mechanism to get started. So for, a completely different fuel, that does pose some challenges, I think. We needed to add new groups, but we've got them in there now, so even for longer chain molecules, same groups should apply. We needed to add new training data. But the good thing about that is that the training data didn't have to be specific to the compounds we were looking at, just had to have the same functional groups. Physical reality checks were useful and found some very quirky aspects of the seed mechanism. Sensitivity analysis was useful. And then what Christian did there was to pick out the important reactions and then look at the literature to see whether there was any high-level theory data or kinetic data that we could use. We are struggling with validation data for this now. Hello, anyone who's got experimental facilities? Because, to be honest, these things have to be coupled together. And what was quite interesting, I don't know if you should film this or not, but actually we tried to predict some data that was in the literature and got very poor agreement from our model, which was weird because we were fairly confident about all the other data we've got. We've seen now this couple of weeks ago, a correction came out for that data. So there was problems with the experiment that has now been redone, and so it'll be interesting to see now whether we get a better agreement. But actually, the model would have suggested in that case that there potentially might have been some issues with the experimental data. So, coupling the two together is very useful. But I don't know, I think maybe some people are using RMG, if anyone's got comments or questions about that. Oh, it's a very good question. My guess is no, but I guess that's where I'll let you know. I guess that's where, what have I done now? I'll repeat the question. So the question was, now that we've added some training data for these functional groups, when we move on to a longer chain version of the same thing, so the butanolic version of the same thing, do we think we'll be able to just run it without a seed? And I guess my answer is, it would be great if that was to work, but I suspect maybe not. But yeah, no, it is a very good question, and that is where we will start, because, in that case, it would only take us a couple of days to generate our new mechanism, whereas producing a seed mechanism means a human interaction in making estimates for the rate constants. So yeah, it's a question. So the question is, did we evaluate the mechanism with respect to intermediate species or just ignition delay time? So, I think the process is ongoing, right? So this is, I'm not going to print these slides because we haven't published this and it's still ongoing work. But Christian was grabbing everything that he could find that was relevant. So yes, there are some intermediate species from this jet stirred reactor data for ethyl levulinate. But as I say, the data in the literature for these molecules, apart from, well, particularly for the levulinates, is pretty sparse. But I think we were pretty satisfied with this actually, because actually the mechanism that was we used as a seed wasn't able to predict very well these concentration profiles, so we were able to improve on that. But, if people are aware of more data, I'd be very happy to try comparisons. I can't hear, sorry. So the question is there any particular reason why diethyl ether is part of the blend? So we're actually basically following on from some work that took place at Trinity, I think in collaboration with Kaust. So they were looking at this ethanolic gasoline blend, and the idea behind it, hopefully I'll get that far today, is that we can tailor the blend through the production process by changing process parameters to give us different percentages of the different blends. And of course, they all have different low temperature chemistry and cetane and octane numbers. And so by tailoring the blend, we should be able to tailor the combustion properties of the blended fuel. The question around ethers is an interesting one. So one of the reason why I think the original ignition delay time data for the blends had to be redone was because diethyl ether is an escape artist, right? And so it's a pretty difficult fuel to handle, which is why I want to move on to the butanol version, because so we've been trying to run some engine tests of these blends, and the diethyl ether is giving us some reliability issues. Well, you're smiling, so you obviously know something about this problem, right? So we've done quite a lot of tests with the butanolic version in the engine and got some pretty good results, including quite large reductions in particle emissions. So it's potentially a way forward. Yeah. Right. Let's see what I've got time left to. So I don't know whether I'll get through everything I've got left, but we'll see what happens. I'll skip some things. Yes. You would have thought this is so hard. Oh, it's going to slide. The shirt is kind of shiny. What was the problem? Was it? Oh, okay. Oh, if I stop moving, will that help? Where was I? Okay, so I mean, in the end, when, we're developing these kind of new fuels or fuel blends or whatever, we're interested in improving on not only the greenhouse gas emissions from fossil fuels, but also other properties. I'm quite interested in air quality, and so any improvements with respect to emissions that impact on air quality are of interest to me. And actually, blending some biofuels can help us in terms of reducing particulate emissions. And that can be categorized for fuels by the Sutton Yield Index. And so this is a plot here showing the Sutton Yield Index for different carbon numbers. And so, well, one of the things you can see is the short chain alcohols are likely to be more effective for reducing Sutton tendencies compared to petroleum type fuels relative to the longer chain molecules. And that might be down to two different effects. It might be down to just dilution effects, so we're diluting what is a shorter chain molecule by blending it with a longer chain molecule, like is contained in gasoline and diesel. And then we might have oxygen effects. So with adding oxygen to the system, it might help to prevent the formation of rich zones, which would lead to the buildup of aromatics and therefore soot. So this was an attempt for a large number of potential biofuels to look at changes in the Sutton index and whether they're likely to be due to dilution effects or due to the additional oxygen effects. So you can see that the additional oxygen effects are larger for some of the longer chain alcohols like octanol, for example. So yeah, we just had a question about ethers as a fuel. So ethers have nice combustion properties. DME and DE have quite high cetane numbers, and they're quite favourable in terms of emissions of particulates, for example, from engines. But they have low vapour pressures, and so they're very difficult. So the smaller ethers are very difficult to blend with liquid fuels. So I'm not sure how far this has got commercially or how far the rollout has got, but actually it was a Volvo that developed a specific DME engine for heavy goods. So basically this is what it required. It required a specific engine that can operate using these low vapor pressure fuels. So I talked about generation earlier. I think I'm going to skip this plot. I did talk a little bit about DME oxidation yesterday and some of the problems that we have in accurately predicting methyl formate in this reaction sequence, but I think given the time I'll skip the complexity of that. Yeah, I think probably the last point to make here is about tailoring fuel blends. So one potential for doing that is with the methyl esters, which will be components of biodiesel. And so again, the chain length, the carbon chain length, and the functional groups and the presence of carbon-carbon double bonds is going to influence the low temperature reactivity of these different fuels. And so here you can see the relative level of conversion of the different fuels over the low temperature range for the different potential biodiesel components. So you can see that the linoleate and the linolenate have a much reduced low temperature reactivity, so very little conversion until we get to about 650 degrees. And that's because they have the presence of more of these carbon-carbon double bonds. And that basically is reducing the low temperature reactivity of these fuels. Okay, so as we move up towards the carbon chains that have less double bonds, then we see more low temperature reactivity. And that might have an influence on how we want to blend fuels and what their overall cetane number of the blends might be. I'm going to skip the bit on fuel runs, sorry. Going on to these tailoring fuel mixtures then. So we said that basically we can tailor biofuels, biodiesel and power to liquid fuels by trying to optimize the process conditions during the production process. So that does give us the opportunity to tailor fuel mixtures, potentially to even optimize that process to give us a final outcome in terms of cetane number, for example, or octane number if we want a gasoline blend. The downside of this is that I showed you that list of fuel properties. There's a lot of properties to optimize. And what we don't want to, I guess, we don't want to find a result which is that there is no optimal blend that will become a drop in fuel to reduce our dependence on fossil fuels. So let's have a look at potential for biodiesel blends. So we've got various different feedstock sources for our biodiesel blends. Sunflower, linseed, corn, or palm oil, peanut, or whatever. And these each lead to biodiesels that have different proportions of the component compounds, which are these kind of long chains with varying numbers of carbon-carbon double bonds. And so that will affect the overall cetane number. So if we take the linoleate, then that's going to have a higher cetane number because it's suppressing the low temperature chemistry. So let's see, one of these. So palm oil, palm oil has a high cetane number. Sorry, we're trying to promote low temperature chemistry. So palm oil has a high cetane number because it has a high proportion of palmitate, which has none of these carbon-carbon double bonds. Whereas if we pick linseed, it's got a higher proportion of linolenate, which has got all the double bonds suppressing the low temperature chemistry, so it's got a lower cetane number. Okay, so potentially then different feedstocks are going to lead to differing fractions of these components, and that does give us a chance to tailor the cetane number to match the diesel that we want to blend with. So we want to be looking at around 50, you know, so a direct biodiesel from a linseed blend would be too low a cetane number for a drop-in fuel, but it could be mixed with a blend from palm oil to give us an overall cetane number that actually meets the regulations. But I would suggest also we need to think about the impact of those choices, of crop choices, on the wider impacts on the life cycle analysis for those fuels, and optimise according to the wider environmental impacts as well. And that's kind of a challenging problem, I guess. So this is data from a paper by Stephen Dooley's group on the ethanolic gasoline blends I was talking about that we were using RMG for. So here, if we look at the derived cetane number, then we're looking in the green and hotter regions because we're looking to get above about 50. And what that means is from a cetane number perspective, to get higher cetane numbers, we're looking to have higher concentrations of the ether compared to the levulinate. But we've said that basically because of the vaporization of ether, that might be challenging for other reasons for our fuels. So cetane number is not the only property that we'll be interested in. If we're looking for potential blends with gasoline, then obviously we're looking at the octane number. And so the opposite's going to apply here, that we're looking at octane numbers, well, typically above RON 95, which is the red region here. And so that's suggesting low components of ether and higher components of ethanol, ethyl levulinate. And so the question is then, can we tailor our production process to produce a blend that has such a high component of the levulinate? And that's the challenge there. I think potentially for the future that blends of hydrogen and ammonia might actually be interesting. So I've said basically that to utilise hydrogen in gas turbines will require a redesign of our injection strategies to avoid problems of high NOx and flashback and all of those things. Our question is that if we blended hydrogen and ammonia, well, sorry, the problem with ammonia, I should say first, is that it's actually a much less reactive. So it has a very low heating value compared to methane. It has a very low laminar burning velocity and a very high ignition energy, so it's not very reactive. So it's a difficult fuel to burn kind of on its own. So, we've got problems with hydrogen because it has, such a high laminar burning velocity and a low minimum ignition energy. So there is the potential to think about blends of these two things to try and, average out these properties. And I guess the question is, I don't know if there's an answer to this really yet or not. Can we come up with a blend of hydrogen and ammonia, or even maybe including some methane, that will allow us to utilise current facilities that we've got, so current gas turbine facilities? Because if we were able to do that, that would be such a massive advantage in terms of infrastructure costs for moving to a low-carbon economy. So I think there is probably quite a lot of effort going into answering this question. Can we come up with a blend of these fuels that will allow us to use current gas turbine designs? Don't ask me, I don't know the answer. I think this is probably ongoing research. I'm not sure why at this point I put in a slide on DNOx, so I think I'll just skip to final remarks at this stage. So there's a huge, I think one of the issues in this field is there are a huge number of possibilities for alternative fuels, either from renewable electricity or from biomass resources. And we need to optimize multiple characteristics to get the best fuel. We want the biggest reductions in CO2 equivalent emissions. We've got to meet physical property requirements for the combustors that we want to use. We might be able to match some of the combustion properties through blending, and then we want to design to minimize emissions from the combustors. So the question is, how do we make optimal choices? If I'm presented with a pile of corn stover, what should I do with it? How do I know what the optimal use of that particular feedstock is? And at the moment, it's an interesting question, and we're gathering data all the time to start to answer these questions. But at the moment, I would say that it's not clear that we have enough data to make optimal choices. I mean, we can make a fuel that works, but is it the optimal reduction in CO2 emissions, and is it optimal improvement in air quality, for example? So it's a difficult question because it can't take us 30 years to figure this out because we haven't got that long. So we've got to get going, and so I guess that's how we're going forward, is trialing things and coming up with things that work, that might not be completely optimal, but are at least along the right road in terms of improvements in overall greenhouse gas effects. So that's it, I think. Bang on time for today. Thank you, everyone.